And today we will be seeing one of the problem from Geeks for Geeks. It says number of valid parentheses. The problem is very simple, that we are given a number n and our task is to find all the valid parentheses of length using only the forward opening bracket and the closing bracket. And we can have such as a valid parenthesis or this as a valid parenthesis. So we are provided a number n and we can get only one valid parenthesis out of it. So quite simple. How can we achieve this one? So there are multiple ways to achieve this problem, but we'll go from the simplest way to the advanced way. So in a way you have n parentheses, let's say. So you can do sorry, you can take 2 to power n combinations. Why 2, by the way? So you have two options, either you close the parenthesis or this is option 1 and this is option 2. Either you open or you close it. There are two options. If there were 3 options, you can take 3 to power n, but yeah, for now it's 2 to power n. So you can have an item like, hey, I have n equal to 2, so I can have 2 closing and 2 opening parentheses. And if I go ahead and open some parentheses, then it says the state becomes 1 opening parenthesis and 2 closing parentheses. Now you have two options. Either you can open yet another parenthesis or close the previous parenthesis. So if I'm choosing the previous option, my parenthesis would look like this and this. Yeah, 2 opening parentheses, which means I'm left with open 0 parenthesis and close 2 parentheses. And if I'm choosing to close this one, it would be like this, which means I'm left with 1, 1. And you got the gist. Likewise, we can move forward and ultimately we can get the count, how many valid parentheses do we have. So yeah, we can go ahead with that. So I can just go ahead and see, return, find the count for n, n parentheses. What is n, n? It is int count of int open and close. So think for a while. Again, we had open and close choices. So either I can open something, okay, either I can open a parenthesis or close a parenthesis. So I can go count if I'm opening, so I'll open -1 because I'm opening it, and close. And if I'm closing it, count, open, close -1. This I can do till the point I receive that, hey, open is equal to 0 and close equals to 0. So if I'm having 0, 0, that means I'm done. I cannot go any beyond. I can return just 1. And yeah, so this I can do. But again, for opening any parenthesis, I have to check that, hey, whether I'm left with any open parenthesis or not. So open should be greater than 0. So I can have then only open. So if I can have open parenthesis left in my ancillary, then only I can go ahead. And same with the close. It's greater than 0, then I can do this. But close also needs to have that close should be greater than open. What does it mean? So that means that either you should have an open parenthesis first, then only I'll close. So if someone comes and say that, hey, my first parenthesis would be closed, then I'll have an open parenthesis, then open, and then close, whatever. But that's not valid. You should open a parenthesis, then only you are allowed to close it. That is how valid parentheses are. And okay, we are doing this, but we are not storing the count. Let's take a variable count, which initially would be 0. I would have cnt plus equal to this, and same here. Ultimately, it would return a count. That's it. Again, the question demands us that, hey, n is a length and n is not the number of open and close parentheses. So if n is a length, I need to have n divided by 2 and n divided by 2, because the open and close parentheses are equal here, and if I'm having n, both are would be n by 2 and n by 2. So yeah, n by 2, n by 2. But if there is a case that hey, n modulo 2 is equal to 1, that means it's an odd number, then in that case I would not have any parentheses, because these are unequal lengths. Or in such case n equals to 0, anything that I'll say less than or equal to 0, then in that case I'll return 0. Cool. This is not very optimal approach, I understand that, but this can get our problem solved. I'll see what can we do better to solve this problem. Sample test case is passed. Let's check for another rest of the test cases. And yeah, this is passed. But we have to optimize this one, right? So you see, we are having 0, 2, 1, 2. If I go beyond in the sense like, hey, I wanted to again go ahead and open this one. So okay, let's do one thing. If it is 2, 2, it's okay. If it is n equal to a bigger number 3, then you can see multiple possibilities like 1, 2, 1, 2 repeating all the times, because you can see right now here 3, 3, and from 3, 3 you can get 2, 3, and from 2, 3 2, 2, and I can have 1, 2, 1, 3, and so on. But the gist of a problem is 1, 2 is liable to come here and is liable to come here as well. So how can we do this? Either we can have a way that we should not recompute this one, and we can store the results already. So this is a very start of a dynamic programming. Now we can store the results. That means we have to store the open and close pointers counts. So I'll have a dp array new and n. What I'll do here is I'll update the n itself, n divided equal to by 2, and that's how I'm avoiding this divide by 2 here, and using a constant n plus 1 and n plus 1. So far so good. Initially I'm going to achieve this with x from dp, and I'll set arrays dot fill x with -1. That means it's unvisited, the result is not yet stored, and I'm going to pass this dp array for computation itself. What this dp array would do, it would store the states already, so you don't need to recompute it again. So I can say count, yeah, I'll take the variable as count and not dp. So if count of open and close is not equal to -1, that means I have already computed it. So I'll return count of open close. Good. And for rest of all the test cases or rest of all the possibilities, I will update this count and then I'll return. So here and here I'll update the count and I'll return. Now it's time to fix the invoking function. Invoking function needs a 2D array, so I'll pass the 2D array which I have named as count. Let's compile this one and check. Well, there are a bunch of errors. So it's not a 1D array, it's a 2D array, my friend. Let's check now. Cool, it passed the sample test case. Let me check for the rest of the test cases as well. Cool, we have did this, and we have achieved this with help of a 2D array. Initially it was 2 to power n time complexity, and now our time complexity went from 2 to power n to O to power O of n. So we are doing only O of n operations and nothing much, but we are requiring a space complexity of O of n as well. Sorry, n square. It's a 2D array, right? We can deduce it, yeah, and the problem wants us to deduce it. So there comes theory of a dynamic programming known as Catalan number. So this problem belongs to Catalan number, which uses binomial coefficient of how many valid possibilities you can generate. It is a very similar operation where you wanted to know that how many possible ways a matrix chain multiplication can happen. So that number, this thing, both comes under Catalan number problems. But for now, this is good. And if you wanted to understand what's Catalan number, do let me know, and I'll make a clear, simple video upon this. That's all about it. For more such awesome content, click the video on your right, and I will see you in the next one.